Hello everyone, welcome to this series of videos on the course Foundations of Mathematics. This is chapter 2 sets, and in part 1 we are going to look at some basic terminologies of sets. So we'll start with the definition. By a set I mean a collection of well-defined objects, alright, and these objects are known as elements or the members of the set. Okay, so by a set I mean a collection of well-defined objects. So let me pick up some examples of some sets. Let's say I pick up a set A and I pick up a set of all students in TY-BSc maths class in Dempe College. Okay, so in this set what is going to come? All the students who are studying TY-BSc mathematics in Dempe College are going to come. Okay, now let's say one more set. I'll pick up a set B and I'll pick up all the states in India, collection of all the states in India. Okay, now when I say well defined, these are examples of well defined collections, because I'll give you an example of something which is not well defined. Let's say I look at uh, top 10 batsmen in the world. Okay, so according to different people, these top 10 batsmen, this collection is going to be a different one. Okay, so this is not a well defined collection, because according to different people, this I won't call it a set, this collection is going to be a different one. Okay, so such collections we don't consider them as sets. So by sets I mean collection of well defined objects. Okay, now notations, usually we denote sets by uppercase letters and we denote the elements of the set by lowercase letters. Okay, so uppercase letters are used to label sets and lowercase letters to label elements in the set. Now supposing I have a set A and X is some object. Okay, I have a set A and I have one object which I am calling X. All right, now this object, if this object X is in A, then we write X belongs to A this way, and this is read as X belongs to A or X is in A. So this notation is used for belongs to. It's a mathematical notation, or you can say is in. Okay, it's in, X is in A. All right, now if the object X is not in A, then we write X does not belong to A. So this is read as X does not belong to A, or you can say X is not in A. Okay, so these are some notations that you all must have already seen in your lower classes. Now how do we represent sets? Okay, so there are basically two ways in which we can represent sets. One is called the roster form, sometimes it is also referred to as tabular form, and the second one is the set builder form. Okay, so we will look at them one by one. First one, roster form. In roster form, all the elements of the set are listed. All right, and the elements are separated by commas and are enclosed with the braces. Okay, so in the roster form what we do, we explicitly list down the elements. Okay, now sometimes it could happen that the list is very long. That time we can use ellipses. These are called ellipses, three dots. Okay, I'll show examples in the next slide. All right. So in the roster form of representing a set, all the elements of the set are listed explicitly. Okay. For example, the set of all integers strictly between 1 and 10 is, I'll name it some notation, let's say capital A, and strictly between 1 and 10. So 2, 3, 4, 5, 6, 7, 8, 9. So what we have done here, we have listed the elements which satisfy this property of lying between 1 and 10, strictly lying between 1 and 10, and we have formed a set. This way of writing a set is called roster form. Second example, set of all even integers between 1 and 2000. Okay, so this set is quite large, right? So you can start from 2, 4, 6, and you can put those three dots, and you can write the last one. Sometimes it may not be possible for you to write the last one also. Okay, so this set B is a set of all even integers between 1 and 2000. Next, set of natural numbers. So I don't have the biggest natural number with me, so I'll write starting few 3, 4 numbers, and I can put the ellipse. All right, so n is denoted by 1, 2, 3, and so on, and the elements they are enclosed in curly brackets. Okay, the set of integers again, so 0 is in between, and on the right hand side I have all the positive integers 1, 2, and so on, and on the left hand side I have my negative integers. So this way of representing sets is called roster form, or sometimes also called tabular form. All right, set builder form. In set builder form, the set is written by describing properties of its elements which are satisfied only by those elements. Okay, so in set builder form, we don't explicitly write the elements in the set. Okay, so what we do, we look out for a common property which all the elements of the set have, and we write the set using that particular property. Okay, for example, you look at this set of all rational numbers, set of all rational numbers, collection of all real numbers x, set of all x in R, such that x is of the form m upon n, where m and n are integers and n is not equal to 0. So we give a property which every element from this set Q, that is the set of rationals, will possess. Okay, so here we do not explicitly write all the elements. So this is the difference between roster form and set builder form. One more, set of all real numbers, set of all real numbers x in R such that x is less than 2 and x is greater than 1 is the set of all real numbers between 1 and 2. So if you put it on the number line, it is actually this. I have 1 here, I have 2 here. I want all the real numbers which are bigger than 1. This, and all the numbers which are less than 2. So all these numbers are in this set capital A. Okay. One more. You form a set capital S of elements of the type XYZ, where XYZ are uppercase alphabets. Okay. So XYZ could be any alphabet from A till Z uppercase, and this is the set of all the 3-letter words in English uppercase alphabets. Okay, now I have 26 alphabets with me uppercase, and I'm picking up 3 at a time, so there will be total 26 raised to 3 elements, these many elements in this set. Okay, so listing this would be quite difficult. So set builder form, in set builder form, this is how the set looks. Okay, empty set. Now you can think of a set as a box which has some well defined objects. Okay, and because I'm thinking of a set as a box, it is possible that that box is empty also. So in the same way, we have a empty set. Okay, so the set that has no elements is called the empty set. sometimes it is also called as a null set, but we won't use the null set here in this course because we are using the word null set for something else also that you all will see in the upcoming lectures. So we will use the word empty set. Okay, so any set which does not have any elements is called an empty set. It is denoted by this notation phi or with the empty curly braces. Okay, so either this or by the letter phi. Okay, so let's look at some examples of empty sets. The set of all real numbers whose square is negative. Okay, the set of all real numbers whose square is negative. Do you know any real number whose square is negative? No. In fact, there is no such real number. So this is an empty set. Okay. One more. Natural numbers which are both even as well as odd. Which are both even and odd. Again, there is no such natural number. So both these are examples of sets which are empty sets. There are no elements in this set. Okay. So one thing you need to take care here is while denoting sets, you either denote them as phi or the empty curly braces. Okay, so these two are the notations for empty sets, but if you write both of them together this way, okay, this will be nothing but a collection of sets. It is actually a set of sets. Okay, and there is one element that is empty set in this set, so this is not an empty set. Okay, so you need to be careful while writing uh, the notations for sets. Okay, subsets. Suppose A and B are two sets. We say that A is a subset of B if every element of A is also an element of B. Okay, and it is denoted by this: A is a subset of B. Okay, so every element of A should be in B. Then only we say that A is a subset of B. So using quantifiers, how do we write this? In chapter 1, we have already seen how to write statements using quantifiers. Okay, so using quantifiers, this can be rewritten as A is a subset of B if and only if for every x in A, x belongs to B. So for every x in A, x belongs to B. Okay. Now if A is a subset of B, then another way of referring to this setup is you can also say that B is a superset of A. Okay. So saying that A is a subset of B and B is a superset of A, they mean the same. Okay, and sometimes we also write this B is a superset of A as this. Okay, it's the same thing. So if you read it from your right hand side, you can read it as A is a subset of B. Okay, now if you have two sets A and B, when will you say that A is not a subset of B? Okay, so you can think on this. You only have to negate the given statement: A is a subset of B. All right, so when will you say that A is a subset of B? You all can think on this. Next is equality of sets. When do we say that two sets are equal? Two sets A and B are said to be equal if they have same elements. So every element of A should be present in B and every element of B should be present in A. Okay. So in other words, A is equal to B if and only if for every x in A, using quantifiers you put it this way: for all x in A, x is in B, and for all x in B, x is in A. Okay, so this is the condition required to say that two sets A and B are equal. And you can again rewrite this as, you can think of this as writing A is a subset of B, and you can rewrite this also as B is a subset of A. Okay, so two sets A and B are equal if and only if they are subsets of each other. Okay, we also saw that every definition is an if and only if condition in the first chapter. All right, now if I have two sets A and B, okay, if I have two sets A and B such that A is a subset of B, okay, A is a subset of B, but A is not equal to B. Okay, when I say A is not equal to B, what is the only possibility now? That means B is not a subset of A. Okay, so whenever A is a subset of B and A is not equal to B, we say that A is a proper subset of B. Okay, so when I say proper subset of B, A and B cannot be equal. So A is a proper subset of B, and we write it as A is a proper subset of B, either this way or this way. There are two ways of writing proper sets. Okay, that means there is an element in B which is not in A. So A and B are not equal, but A is a proper subset of B. Fine. That is, A is a subset of B if and only if there exists X in B such that X is not in A. Okay, so A is a proper subset of B if and only if you can find one point in B which is not in A. Then B won't be a subset of A, and hence A will not be equal to B. Right? Now, the set of integers Z is a proper subset of rationals. Z is a proper subset of Q. Okay, so quickly we'll give a argument for this. First, we will show that Z is a subset of Q. Okay, so how you show that one set is a subset of the other? You take one element in the first set, and then you show that that element is there in the second set also. Okay, so let me pick up one arbitrary integer. Before that, how we represent rational numbers? Rational numbers is nothing but the set of all real numbers x such that x is equal to m by n, where m and n are integers and n is not equal to 0. Okay, we know this is the set of rational numbers. So what I'll do, I'll pick up one element in Z here. Let k belong to Z. Okay, so then I can always write k as k by 1, because k by 1 is equal to k. That means we have expressed this integer k as some integer upon some integer where the denominator is not equal to 0. That means this integer that we picked up, it satisfies all the properties of rationals, so it is there in the set of rationals also. That means k is a rational number, and hence this proves that Z is a subset of Q. So all the integers are present in rationals. In fact, every integer is a rational number. Okay. Now to say that Z is a proper subset of Q, will have to find one rational number which is not an integer. Okay. So if you pick up one element in Q which is not in Z, then we are done. Okay. So any fraction which is not an integer, let's say half. So if you pick up x equal to half, that's a rational number, but it is not an integer. So we found one point in Q which is not in Z. Okay, so Z is a proper subset of Q. I hope this is clear. Next, and this is an exercise that I'll leave for you all. What you all can do is try to show that set of natural numbers is a proper subset of integers. Integers is a proper subset of rationals. Okay, this is already done. And set of rationals is a proper subset of the real numbers. Okay, so this we can discuss during the live session. Okay, now can we say that empty set is a subset of every set? Will it be fair enough to say that empty set is a subset of any set? So supposing I pick up one set, supposing A is any set. So what we claim is empty set is a subset of this set. Okay, so to say that empty set is a subset of A, we'll have to show that every element in the empty set is there in A, right? So we need to show that the statement is for every x in the empty set, x is there in A. Okay, now if I want to show that this statement is a true statement, one of the ways to do that is you show that its negation is false. So we consider not A. So how do you negate this? There exists x in empty set such that x is not in A. So the negation of this is there exists a point x in the empty set such that x is not in A. Now this is a false statement because this is telling me that there is a point x in the empty set, and we know that empty set cannot have any points, right? So that's a contradiction here. That means this set and this statement not is the negation of the given statement is false, and hence that forces the given statement to be true, and hence empty set is a subset of every set. Okay. Now again another exercise for you all. What you all can do is you try to express empty set as a subset of rationals in two different ways. Okay. And also the empty set is a subset of real numbers in two different ways. Okay. So think over this, expressing empty sets in these ways, which we can discuss during the live session. Okay. Now look at this example. Identify this set. Let's see which elements are coming in this set. Okay. Supposing I am having a set capital A, which is collection of all real numbers x such that x plus 1 by x is bigger than or equal to 2. So a number plus its reciprocal should be bigger than or equal to 2. Okay. So is there any better way of writing this so that it's easier to see which elements are actually present in this set? Okay. Now first thing that we should ask ourselves is, can 0 come in this set? No, because I'm having term which is 1 by x, and if I take x equal to 0, then this 1 by x won't be defined. So definitely 0 is not coming, right? So 0 is not there. What about negative numbers? Can negative real numbers come in this? If I pick up some negative number here, then this x is negative and 1 by x also will be negative. So I'm having sum of two negative numbers which will be again negative, and I'm saying that 2 is less than or equal to a negative number, again which is not possible, right? So any negative number cannot come in this. Okay. So the only real numbers which are left out now are positive real numbers, because 0 cannot come, the negatives also cannot come, right? So if x is negative, then x cannot lie in A, even 0 is not lying inside A. So supposing x is positive now, okay, supposing I look at the case when x is a positive real number. So we look at this expression, x plus 1 by x is bigger than or equal to 2, okay, and we will try to simplify this. So x plus 1 by x is bigger than or equal to 2. That will happen, okay, that will happen if and only if I can multiply this inequality throughout by x, because x is positive, inequality will remain the same. So that will give me x square plus 1 is bigger than or equal to 2x, which again I can represent as x square minus 2x plus 1. Okay, shift 2x this side, and that will be bigger than or equal to 0. Okay, and this again I can rewrite as x minus 1 the whole square is bigger than or equal to 0, and this is always true because square of any real number is always bigger than or equal to 0. That means if x is positive, then it will satisfy the condition that is required for that element to be in A. Okay, this condition it is going to satisfy. So if x is positive, then x is in A. Hence the set A which is given to us is nothing but the set of all positive real numbers. So set of all real numbers x such that x is positive. Okay. Next is intervals. Supposing I have two real numbers a and b. Okay. Then there are many intervals in R. So I will list them one by one. This one is called a closed interval. Okay, and it is denoted by this closed brackets and a comma b. Okay, and it is defined as the set of all real numbers x such that x lies between a and b, and it can be a as well as b. Okay, so if I put it on the number line, it will be somewhat like this: a is here, b is here. So all a is included, all the numbers between a and b are also included, and even b is included. Okay, so whenever the endpoints are included in the set, we use the square bracket. Okay, so that is called the closed interval. Second one is the open interval. The difference between these two is that in the open interval the endpoints will not come. So I'm looking at all the real numbers which are strictly lying between a and b. Okay, this is called an open interval. Next, I have a closed open interval. So this will be closed at one end and open at one end. Okay, so because it is closed on the left hand side, it is named as closed open, closed word first. So all the elements which are bigger than or equal to a but strictly less than b. So they can be equal to a on one side, but they have to be strictly less than b on the other side. Okay, as you can see here. So this is closed open interval. In the same way, we have open closed interval. So in this, on the left hand side, I have open, and on the right hand side, it is closed. So all the real numbers which are strictly greater than a and which are less than or equal to b. Okay, this is called open closed interval. Now look at this. This is called a closed ray. Okay, why it is called so? Because here I am looking at all the numbers, real numbers, which are bigger than or equal to a. Okay, and they can keep on going. Okay, they keep on going. So I'm looking at all the real numbers x such that x is bigger than or equal to a. So if you want to put it on the number line, if you have your number line here and a here, so all these you can consider. Okay, this keeps on going. It's a infinite set. Okay, so this is called a closed ray, and you can have it from the other side as well. So minus infinity comma a and closed at a. Okay, so these two sets are called closed rays. In the same way, we can have open rays also, wherein the point a is not included. Okay, so all real numbers x which are bigger than a will be coming in this interval a comma infinity, and in the same way minus infinity comma a you can define, and these two are called open rays. Okay, now these two exercises you all can try. Now when I'm talking about intervals, for what choices of a and b, the above intervals, I mean the intervals on the previous slide, they are non-empty. Okay, so for what values of a and b these intervals will be non-empty, that you all think. Okay, how many conditions should a real number x satisfy to belong to this open interval? So if I say x is there in this interval, how many conditions should that x satisfy? Okay, next question is, how many conditions should a real number x satisfy to belong to this open ray a comma infinity? Okay, so you all can think over these questions. One more is, if a and b are two real numbers and a is bigger than or equal to b, then you identify the following subsets of R on the real line. So I have given some intervals here. What you can do is you try to plot them on the real line and you see how it looks. Okay, we are given that a is bigger than or equal to b. Okay, now let's look at an example. Okay, a set is given to us. Okay, a set is given to us, and the set A reads set of all real numbers x. Okay, set of all real numbers x such that modulus of x minus 2 minus modulus of x minus 4 is equal to 3. I need to pick up all the real numbers x which satisfy this equation. Okay, so if you observe closely, modulus is coming twice here. I have one modulus outside, and inside that I have two terms, each one is having a modulus and separated by the negative sign. Okay, separated by the negative sign. So let's try to identify this set, which real numbers will satisfy this equation. Okay, now if you look at this, I'm having modulus of x minus 2 and modulus of x minus 4. So the values of these two numbers, they will change as you move across 2 and you move across 4. Okay, so to get the idea of this, I will just put the numbers 2 and 4 on the number line. Okay, 2 is here and 4 is here. Now when I'm looking at numbers which are less than 2, which are here, any number which is less than 2 from here. Okay, now if x is less than 2, then x minus 2 would be negative, and if a number is less than 2, it is also less than 4, so x minus 4 will also be negative. Okay, whereas if I pick up a number here in between 2 and 4, okay, in between 2 and 4, then x minus 2 would be positive and x minus 4 would be negative. And if I pick up a number which is bigger than 4, then x minus 2 as well as x minus 4 all will be positive. Okay, so we will divide this problem into three parts, three cases. One is numbers which are less than 2, numbers which are between 2 and 4, and numbers which are bigger than 2. I hope that's clear. So the modulus changes the sign in the interval at 2 and 4. So we consider these three cases. X is less than or equal to 2, x lies strictly between 2 and 4, and x is bigger than or equal to 4. In case 1, x is less than or equal to 2. Now because x is less than or equal to 2, x minus 2 will be negative and x minus 4 will also be negative, right? So x minus 2 is less than or equal to 0 and x minus 4 is also strictly less than 0, right? So because this is less than or equal to 0, its modulus will be its negative. So mod x minus 2 will be minus of x minus 2, and again x minus 4 is negative, so its mod will be negative of itself, so minus x minus 4. So when I put it in this equation, modulus of mod x minus 2 minus mod x minus 4, that will give me, this part is minus of x minus 2, that's here, and this part is minus of x minus 4, and that minus into this minus will give you plus in between, so I have x minus 4. Okay, so if you simplify this, x will cancel off and you have modulus of minus 2, which is 2, and it is not equal to 3. That means if you pick up any number which is less than or equal to 2, that number will not satisfy this equation. Okay, that number will not satisfy this particular equation. That means none of the numbers which are less than or equal to 2 will come in this particular set. Is it clear? So no such x belongs to A. So if a number is less than or equal to 2, it won't come in this set A. One case is done. Case 2, supposing x lies between 2 and 4, strictly lying between 2 and 4. Okay, so if you put it on the number line, you will have something like this with you. 2 is here and 4 is here. I have the number x here. So x minus 2 would be strictly positive and x minus 4 would be negative here. Okay, so how will this equation look like? Mod x minus 2 is positive. So x minus 2 is positive, so its modulus will remain as it is. Whereas x minus 4 is negative, so its modulus will be negative of itself. So that will become plus x minus 4. And that will give you modulus of 2x minus 6. Okay, so directly from here we cannot decide now whether the points from this case which are lying between 2 and 4 are coming in the set A or not. Okay, so we'll have to analyze this further. Okay, so let's do that. Now x lies between 2 and 4. Okay, that's what our second case is. X lies between 2 and 4 here. So x is greater than 2 and x is less than 4. Okay, so if I look at this number 2x minus 6, okay, which I've obtained there on the right hand side, then x is greater than 2. Okay, so I can put it this way, x is greater than 2. Now I can multiply 2 on both sides, so 2x will be greater than 2 into 2. Now I subtract 6 on both sides, so that will be this, right? So 2x minus 6 is strictly bigger than 2 into 2. This is coming because x is strictly bigger than this 2. So that we replace, that inequality I replace here. So this is less than 2 into 2 minus 6, sorry, bigger than 2 into 2 minus 6, and that is 4 minus 6, that's minus 2. Okay, so 2x minus 6, it is greater than minus 2. And also if you use the second half of this inequality, x is strictly less than 4, then 2x minus 6, x is less than 4. So again I multiply 2 on both sides, so 2x will be less than 2 into 4, and again I subtract 6. Okay, So 2x minus 6 is strictly less than 2 into 4 minus 6. Okay, so that is coming because x is strictly less than 4. So I replace x by 4. The resulting output that you are getting here will be bigger than this because 4 is bigger than x. And this is 8 minus 6, that's 2. That means 2x minus 6, it lies between minus 2 and 2. Okay, so 2x minus 6, it lies between minus 2 and 2. So it is of the form minus x is less than a is less than x. So using the properties of absolute value, modulus of this number would be strictly less than 2 because I am using this property here. If x lies between minus a and a, then modulus of x will be strictly less than a. Okay, this is one of the results that you all have studied in the calculus course. So that means the modulus of 2x minus 6 is strictly less than 2, and this equation here, whenever x lies between 2 and 4, is equal to 2x minus 6, modulus of 2x minus 6, and this is less than 2. So definitely it is not equal to 3. That means again none of the points which are strictly lying between 2 and 4 will come in your set. Okay, so now such x will belong to A. Okay, I hope this is clear. See, last case is whenever x is bigger than or equal to 4, what is going to happen? Okay, so if you put this on the number line, I have 2 here, I have 4 here, and I'm looking at numbers which are bigger than or equal to 4. Any number which is here. So it is bigger than or equal to 4 and bigger than 2 also. So x minus 2 will be strictly positive and x minus 4 will be bigger than or equal to 0. So if I try to look at that equation, modulus of mod x minus 2 minus mod x minus 4, so that will be x minus 2 minus x minus 4. Okay, so this is positive, so it will remain as it is. Again, this is bigger than or equal to 0, so it is going to remain as it is. And if you simplify this further, that will reduce to 2 modulus of 2, which is 2, and this 2 is not equal to 3. That means even in the third case, whenever any real number x is bigger than or equal to 4, such a real number cannot come in the set A. Okay, that means the set A that we started with is a empty set. Okay, so the set A cannot have any elements. A is a empty set. So this is how you given a set in a set builder form, you can break it down into cases whenever you have modulus, and you can explicitly find what are the elements of the set. Okay, these are some exercises for you all, similar ones which I have done in the previous slide. Identify the set B of set of all real numbers such that this modulus is equal to 2. So these are similar ones which we have already discussed. Okay, so we can have a look at these in the live session. Okay, so if there are any questions, you can put it in the comment box. These are my references. Thank you.